Hi, and welcome to this tutorial looking at the forces between molecules. So in the previous tutorial, we were looking at polarity, so bond polarity, and how to identify whether a molecule is polar or not. And mostly that revolved around electronegativity. This time we are having a look at intermolecular forces and their properties, permanent dipole-dipole forces, induced dipole-dipole forces, which can be called London or Van der Waals forces, depending on your specification, and hydrogen bonding. So we're going to be using our knowledge to do with shapes of molecules, the polarity, and our previous tutorials on this. So make sure you've covered those videos before coming on to this tutorial. So intermolecular forces, they're not intramolecular. So we're not talking about the covalent bonds or ionic bonds between two individual atoms. We're talking about international, the bonding between different countries. We're talking about international, bonding between different molecules. So if we've got two molecules of water, how do they interact with each other? Two molecules of carbon dioxide, for example. So there are three types of intermolecular force that you need to know about. We've got permanent dipole-dipole forces, induced dipole-dipole forces. That's one of the ones that have got a couple of names, London or Van der Waals, and then hydrogen bonding as well. Now, if I was to put these in order, I'd put induced first because this is in a slightly counterintuitive order. Really, induced dipole-dipole forces are the weakest. Then we've got permanent dipole-dipole, and then we've got hydrogen bonding as the strongest. So I think that's more of a logical order here. And intermolecular forces are going to always be weaker than metallic bonds, ionic bonds, and covalent bonds, because those are intramolecular bonds. So remember, we're thinking about a slightly different thing. So intermolecular forces, they dictate melting and boiling points mostly. So whenever you hear melting and boiling, you're thinking of intermolecular forces. You know, when you boil water, we do not break the bonds between the oxygens and the hydrogens in the water molecule. We're breaking the intermolecular forces between different water molecules. So it goes from liquid to gas. Okay, so you do know some of this stuff. It's just putting it all together. If we've got a particular compound or a mixture and it's got polar molecules in that mixture, so HF, for example. So I've got lots of HFs in a bag, and each HF is covalently bonded, and we talked in the previous tutorial about the fact that fluorine is more electronegative than hydrogen, so it's going to hold that pair of electrons closer to itself, which is going to give it that partial negative charge, that delta negative. So what we're going to end up with is what we call permanent dipole-dipole forces between the delta negative fluorine of one HF molecule and the delta positive hydrogen of another HF molecule nearby. Okay, so that is a permanent, because that dipole is always there. So they're called permanent dipole-dipole forces. So if I simplify that, and I've got just a bag of HFs everywhere, and they're at all different angles, then we're going to end up with our permanent dipole-dipole forces between these. Okay, because this is going to be delta negative and these are all going to be delta positive. And of course, negatives and positives attract, unsurprisingly. We know this from a long time ago. I've got an image here with a charged rod. So you might remember this from static experiments that you've done at GCSE. And you will find that a polar liquid, like water, remember we said it's polar because it's non-symmetrical, and the attractive forces are always stronger than the repulsive forces between the rod and the molecules. So if we charge the rod as negative, it's going to attract the delta positive hydrogens of the water molecules. And the way we charge that, if you remember from GCSE, is we can use a cloth, for example, to rub the rod and transfer those electrons. And you'll find that liquid is attracted to the rod because water is made of polar molecules. And so the negative charge is going to be attracted to the delta positives on the hydrogen. What about induced dipole-dipole forces, also known as London forces or Van der Waals forces? Now, Van der Waals has gone out of fashion in some specifications. So on OCR, for example, we call them London forces. And sometimes they're called dispersion forces as well. So there's lots of different names. So it's good to know if you're using different textbooks and online examples to know that we call them all sorts of different things. And they are present between atoms and molecules that do not have polar bonding. Okay, so between Cl, same atom, the electrons are held perfectly in the center. We don't have any polarity here. But when two non-polar atoms comes toward each other, the electron clouds of those, they're going to repel. We've got two chlorine atoms, and they are bonded to each other in a covalent bond. And yes, The covalent, the bonded electrons are held directly in the center. But there's also lots of other electrons around those chlorines. They don't just have one electron, they've got quite a few. And electrons move randomly in space and time in areas of probability. And at any one split second, we might find that we will find there are more electrons on one side of the Cl2 molecule than the other. So on one atom more than the other, just by chance. And that's called a spontaneous dipole. And any molecule can do that because electrons move randomly, unpredictably. And so they can be on more than one side than the other, okay? So that's a spontaneous dipole. Now, in one chlorine molecule, which I'm going to draw like this, spontaneously, if I show this as the electron cloud, my red, has more electrons by chance in a split second on one side of the molecule than the other, that is going to create a spontaneous dipole. It's going to make that chlorine more electronegative than the other side, even if it is for a nanosecond. Now, if there's a neighboring chlorine molecule nearby that comes across this, it's going to induce this molecule here is going to induce a dipole in this nonpolar molecule. You can imagine if I've got a high area or a higher area of electron negativity on this chlorine molecule, what's that going to do to this chlorine molecule here? It's going to repel the negative electrons away. So it's going to push the electrons away onto the other atom, and it's going to leave that chlorine feeling electron deficient. And it's going to leave this chlorine with those extra electrons that have been pushed away. Okay, so what's happened here, the way I describe it is we've got a spontaneous, just by chance, spontaneous dipole that's formed because of the random asymmetrical movement of electrons. And that has induced a dipole, a temporary dipole. It's not permanent, it's temporary, in a neighboring molecule of chlorine. Okay, so that's how I describe what's happened. Now, this happens in a split second, so that can immediately disappear again. Okay, because it's all temporary, as opposed to permanent dipoles, which are permanent. Okay, so that's what we call induced dipoles. I've induced a dipole in a neighboring molecule. Let's look at more examples. Okay, so the first thing I said is we've got the electrons being equally shared, but at any split second, we have a sudden displacement of electrons in one atom to one side. So we've got a temporary dipole. It's spontaneous, it's by chance, it just happens because of life. The dipoles are temporary and are constantly being created or destroyed at any split second. They're all over the place. A dipole is always there at a given time, okay? Because electrons will always mathematically be more on one side than the other of an atom, just because of the movement of electrons. They can't possibly actually be held perfectly in the center. They're incredibly small and whiz around a lot, okay? So you can see I've got an example here of where we've got a temporary dipole forming, and then I've got a different type of temporary dipole. And it is inducing a dipole in a neighboring chlorine molecule. So because we've got this spontaneous dipole formed here, the positive electrons, it's going to attract, because it's electron deficient, it's going to attract electrons from a neighboring molecule towards it, and it's going to cause a dipole in the next molecule. And an iodine lattice is a good example of this, because I2, iodine, the electrons are equally held between the two, okay, but the iodine lattice is made up of many iodine molecules held together by induced dipole-dipole forces. The fact iodine can be a solid proves that we can get intermolecular forces even though we've got non-polar iodine bonds. And so the induced forces are created in the same way. We get a spontaneous dipole formed, and that induces, it's temporary, and it induces a dipole in a neighboring iodine molecule. And that happens en masse. And when that happens with millions, millions, and billions of molecules, it has a big impact on the structure and the physical properties. So then we've got hydrogen bonding as well. If you do biology A-level, you'll come across this, usually quite near the start of the course, but you need to make sure that you know what the chemistry A-level syllabus needs and what the biology A-level syllabus needs in terms of exam technique. They do slightly differ. So the hydrogen bonding, it's only formed when we have hydrogen, oxygen, and nitrogen. So some people memorize that as NOF, NOF. So we need to have one of those atoms present. Okay, and of course we need hydrogen as well, hydrogen bonding. And NO and F, each of these atoms are more electronegative than hydrogen. Okay, so they attract the electron pair in the bond. So if we're looking at an OH bond here, then oxygen is more electronegative, so we're going to leave the hydrogen with a delta positive charge and the oxygen with a delta negative charge. And the orange electrons are part of the covalent bond. As shown, they're held more closely towards the oxygen than the hydrogen. And we've got the green lone pairs up here. They're not going to do anything. But they do affect the shape, of course, of the molecule, hence why we've got that non-linear shape with 104.5 as my bond angle. Okay, so the hydrogen atoms have got a high charge density as they've only got one shell of electrons, And then we've also got a delta positive charge. They're electron deficient. So they're going to attract the lone pair of electrons on a neighboring water molecule. Okay, and they're going to form these red dots here, which are intermolecular forces, and they are hydrogen bonds. We've got hydrogen bonds occurring. So you will get hydrogen bonds in terms of organic chemistry when you've got an amine. That's going to allow hydrogen bonding to happen, because if I've got two amine molecules near each other, I'll just draw them here. We're going to end up with a delta negative on the nitrogen because it's more electronegative, which is going to leave the hydrogens electron positive, and that NO or F has to have a lone pair. So it does. So there's a lone pair here, there's a lone pair here, and so we are going to be able to form a hydrogen bond between the lone pair on a N here and the delta positive hydrogen, the electron deficient hydrogen on a neighboring molecule. So that's an example there. And then also with alcohols, so OH, and then if I have another molecule over here, now, each of those O's has got a lone pair, so that's what we need for hydrogen bonding. And we also have a disparity in the polarity. So the oxygen is more electronegative than the hydrogen. Great. So now I can form two hydrogen bonds here. So remember the conditions, it has to be NO or F, so it's an O. There has to be a lone pair on the NO or the F, and there's a lone pair on this oxygen, and it can only form a hydrogen bond with an electron deficient hydrogen, and that hydrogen is electron deficient. So there's one and there's another. So we've got two hydrogen bonds being formed there. So our permanent dipole-dipole forces are stronger than London forces or induced forces, but they're weaker than hydrogen bonds. Okay, so this is quite a good way of learning it. In terms of strength, we start with our London forces, the weakest. Then we get permanent dipole-dipole. This one's often ignored. Don't ignore it in exams. Remember they exist. Often in exams, we tend to focus too much on London or induced and hydrogen bonding, but there is permanent dipoles in the middle. And then hydrogen bonding is the strongest type of intermolecular bonding. It requires the most energy to overcome. And like I said, London forces is the weakest. It's found in nearly all molecules. The only place you're not going to find it really is going to be giant covalent structures. They don't have intermolecular forces, for example. Any giant structure does not have intermolecular forces, only intramolecular. But in any type of molecule, including the noble gases, okay, so xenon, argon, etc., and just atoms by themselves will exhibit London forces. And non-polar molecules will only have London forces. And we also get them in long chain alkanes because there's lots of CH, bonds all the way along. So they're going to be very non-polar. So we're going to be seeing a lot of these types of forces. Okay. And then they often need to be broken upon boiling or melting, but it doesn't require as much energy as the other forces. And then we've got hydrogen bonding as the strongest. That requires a lot more energy to overcome. And it's what gives water, in terms of in the oceans, a lot of the properties that it has. So in terms of surface tension and high specific heat capacity. When we're talking about induced dipole forces, or London forces, or van der Waals forces, or dispersion forces, all of these terms, we are thinking about, let's just call it London forces, or most specifications, that's what it's called. We're thinking about the molecular size, molecular shape, and the molecular distance. That is what dictates the strength of the London forces. So a larger molecule, so for example, a very long chain hydrocarbon is going to contain more electrons in its structure. Therefore, we've got larger electron clouds. And the greater the number of electron clouds, the stronger the London forces, the stronger the induced dipole-dipole forces, and more energy is required to overcome and break those forces. So therefore, longer chain hydrocarbons, or just bigger molecules that have got London forces, have got higher melting and boiling points. If molecules compact closely together, so they're not branched, this is more to do with organic. If they're not branched, they're just like linear chains, they compact very closely together, they're going to have more points of contact with each other. And so they're going to have stronger intermolecular forces between the layers. So yeah, for example, unbranched straight chain alkanes compact closely together. So they also require more energy to overcome and will have higher melting and boiling points. And then the further apart the molecules are, so that links to our previous slide, the further apart the molecules are, because of maybe their state and their branching, for example, the weaker the intermolecular forces, the less energy it takes to overcome, and the lower the melting and boiling point. So if we compare two hydrocarbons here, we've got pentane, which is a long hydrocarbon chain, and we've got a branch chain of methylpentane. Both contain the same number of electrons because they both are just structural isomers of each other. But pentane's got a higher boiling point because it's got stronger London forces, because the molecule is unbranched and it's a straight chain. So molecules of pentane can pack more closely together than loads of molecules of 2-methylpentane. And here is a graphical description of what's going on. So you can see that straight chain alkanes versus branch chain alkanes, we've got that higher average boiling point. And it also increases as the chain gets longer. So the number of carbon atoms in the chain, as it gets longer, we're going to get higher and higher because we're getting more and more electrons. Okay, because the more electrons are stronger, the induced dipole-dipole forces, the stronger the London forces, and the boiling point increases. In exam questions, it's really common for you to be asked to explain the difference between the melting and boiling points of two molecules. And of course, when you see melting and boiling point, you are thinking intermolecular forces. So you're thinking London forces, permanent dipole-dipole, or hydrogen bonding. That's what you need to be thinking in your head, nothing else. So you need to be clear and state which forces are present. For example, if we're comparing a 3-carbon compound like propane and a 2-carbon compound like ethane, you can say that neither have permanent dipole-dipole forces. Okay, because what they contain is just CH bonds and CC bonds, both of which are considered non-polar. Okay, so we don't have permanent dipole-dipole. We don't have hydrogen bonding. Although we have hydrogen present, we don't have NO or F present, and especially then we don't have any lone pairs. We also don't have an electron deficient hydrogen present because the CH is not is non-polar. Okay, so we don't have any of the conditions for hydrogen bonding, so we definitely don't have that happening. And then we need to consider London forces. So ethane is 2-carbon and propane is 3-carbon. So propane has got more electrons, it's a larger molecule, so it's going to have stronger London forces. And be really careful with your exam technique. You need to use comparative language. So we can't just say that propane has strong London forces and ethane has weak. We need to say propane has stronger London forces and propane has weaker London forces. So propane requires more energy to overcome and break those intermolecular forces. So it's got a higher melting and boiling point. Can you see I'm adding less, more, stronger, higher, weaker? That is what we call comparative language. It's essential for exam technique in these sort of questions. It's really frustrating when we know a student knows the answer. They know that it's got stronger London forces, but they just use the word strong. It's got strong London forces. We can't credit that. So make yourself a note. That's something that's often not given in the textbook. It's really, really important. Let's consider the hydrogen bonding then in hydrogen halides. So we know that hydrogen bonding is the strongest type of intermolecular force. It requires a lot of energy to overcome, more energy than the others. So higher melting and boiling points. So if we look at the graph, we've got hydrogen fluoride is a lot higher in terms of its melting and boiling point than the other halides. And this is due to the presence of hydrogen bonding because we've got Cl, Br, and I. They're not going to be able to form hydrogen bonding because it's not NO or F. So we haven't got an N, an O, or an F in the others, but with HF we do. We've got fluorine. So HF, if that molecule comes across another HF molecule, we've got that polar bond going on here, and we've got a lone pair on each of the fluorines, and so we can form hydrogen bonding between them. Okay, so we've got hydrogen bonding. And the hydrogen bonding significantly increases the boiling point. Okay, even though HF is actually quite a relatively small molecule, it overrides the fact that hydrogen bonding is the strongest type. We've noticed that we've got a particularly high boiling point for HF because of the hydrogen bonding, but we've also got this increase between HCl, HBr, and HI. Now, all of these have got permanent dipole-dipole intermolecular forces, but they've also all got London forces. And so the larger the molecule, the stronger the London forces, the more energy it takes to overcome, the higher the boiling and melting point. HI is a much larger molecule than HCl, so it's going to have much stronger London forces than HCl. So there's two patterns here. We've got the high here, and then we've got the increase as we get a larger and larger molecule. As I said, the London forces, although we were talking about permanent dipole-dipole in the previous image, London forces as well are going to increase in strength as the molecule increases in size. So you can see here, if we've got, we said that we do have hydrogen bonds in HF, but we don't in the others. We've got permanent dipole-dipole forces in HF, and we've got London forces as well, because London forces we're going to have in all of them. Okay, in all of them. And in permanent dipole-dipole, we're going to have them in all of these as well. What we can say is that we're going to have the strongest London forces in HI. Again, let's talk about exam techniques. So when we're discussing the types of intermolecular forces, make sure you're really specific. So don't just say something has hydrogen bonding, therefore it's the strongest. Talk about it. So HF, the hydrogen bonds form between the delta positive and the delta positive hydrogen and the delta negative fluorine that's got a lone pair. You will often find, especially on OCR, that drawing out the hydrogen bonding is going to be the quickest way to obtain your marks. You have to include the delta charges on them, and you have to include the lone pair, and you have to label the hydrogen bond. So this, you would lose a mark for this structure. You have to label hydrogen bond. Just having a red dotted line, of course you can't use colour in an exam, but just having a dotted line isn't enough. You have to actually label that bond. You need to tell them you know the difference between a covalent bond and an intermolecular force. Okay, so examiners are always immediately impressed with diagrams. It gets you marks much quicker than writing a written explanation of hydrogen bonding.